We saw that chaotic systems in some sense are like random systems. The dynamics is deterministic, you specify the dynamics completely, and yet the outcome looks fairly irregular, aperiodic, and has many of the characteristics of completely random motion. Some of the models we looked at, like the Bernoulli shift, I even mentioned casually, could be as random as a coin toss itself, and let us try to substantiate this in some sense and make some statements regarding how random deterministic dynamics can get. Recall the Bernoulli shift, which is our prototypical model for random for deterministic chaos, which involved taking an initial condition, writing it in binary in the form A2 etc., which would imply that x1 is 2x naught modulo 1 becomes 0.a1 a2 and so on, and this keeps getting iterated, and each time you shift this decimal point one place to the right and throw away whatever is to the left of it, and this was the Bernoulli shift, which was chaotic with a Lyapunov exponent equal to the log of 2, the natural log of 2, and that was positive when we said the system was chaotic. We could now ask the following question: is there a way of partitioning the phase space in the problem? In this case the phase space is just the unit interval between 0 and 1 in such a way that I keep track of not the precise point at any stage, but merely where it is in one of the cells in phase space, and given that information, namely where the successive iterates are, can I reconstruct what the original map is? And the answer in this case is yes, and we do it as follows. So I start by saying that the unit interval, and here is the map function, slope 2 here, I break up the unit interval into two sub intervals, 0 to half and a half to 1, and if the representative point is in the left I call it L, if it is in the right I call it R. So I will call this portion, this is a half, I will call this portion L and this portion R, and it is immediately evident from here that if the leading digit is a 0 then you are in L because the number is less than a half, and if it is a 1 then you are in R on this side. Now if I merely keep track of whether the representative point, the iterate at any stage, is in the left bin or the right bin, these two cells, and I keep track of this and write this sequence down next to each other, what would I get? I would get after a long time a string of L's and R's. Yeah, absolutely, you are not saying anything, I mean you are simply saying that it is in the left or in the right, and I am not worried about the rest of the digits. Then if I keep track of that, this is called symbolic dynamics because I associate with each cell a letter of some alphabet and keep track of where the representative point is, in which cell it is at each iteration, and I get a long string of letters of the alphabet. In this case the alphabet has just 2 letters. Now if I took a typical point which is not part of a periodic cycle and iterated it over a long time, this is what the string would look like completely, and the sense in which deterministic chaos is like a random number generator is the following. In this case, given any string of this kind which arises by iterating the Bernoulli map for a specific initial condition, given any such string, the statement is there exists a sequence of coin tosses where I write L every time I get tails and R every time I get heads, which is indistinguishable from this sequence. So the statement I repeat is that given any string which has been generated by iterating a typical initial condition, a generic initial condition, and I get a sequence of L's and R's, and now I do not tell you where this sequence came from. The point is there exists a sequence of coin tosses which are supposed to be completely uncorrelated and random, which would produce exactly the same string, and in that sense the outcome, you can't tell whether this outcome came from a purely random machine like a coin or from a purely deterministic rule of evolution for a certain initial condition. Yes?
When you say there exists a sequence,
yes,
that only means there is a one-to-one mapping between the strings.
absolutely, there is a one-to-one mapping.
Bring about randomness into it?
No, the point is you would think that when you have the result of deterministic evolution, you would think that you would see some pattern in it. You would immediately mean it cannot be quote unquote truly random, there is some kind of pattern in this whole business. But the point I am making is that the evolution, the result of the evolution of a completely deterministic rule, just by looking at the end product you cannot tell whether this originated from a purely random machine like a coin, tossing a set of a coin repeatedly, or whether it came from some applying some deterministic rule.
Like the
So
probability of the sequence and the probability of the sequence.
well, the probability of each of these sequences is exactly the same. Every sequence for a coin is equally probable, and the point is that while one would think that deterministic evolution must necessarily lead to some order, some kind of pattern which you would see in the final result, the answer is no, that is not necessarily true. If this were periodic, if this were part of a periodic orbit and so on, there would be a pattern which would emerge immediately. You would see this and say, aha, this couldn't have been pure chance. But the fact is even that is not true, because after all even this sequence could well have been the result of a set of coin tosses. So determinism and randomness as we understand it naively are kind of intricately bound with each other, and just by looking at the product of just by looking at the outcome of evolution, one cannot tell whether it came from a random sequence quote unquote some random dynamics, or whether it came from something which was purposeful and periodic and regular. So this thing gets blurred, this distinction gets blurred, and in that sense the Bernoulli shift is as random as a coin toss, because the typical sequences it produces are as random as that of any coin toss. Yeah. Now we are getting deep questions. What is the definition of randomness? This is tricky. It is not possible to define a truly random sequence to full satisfaction. It is not possible to do so. We can only give measures of randomness and find out if our strings meet those requirements or not. For instance,
I don't understand the word.
yeah, exactly, he does not understand the meaning of the word random, and I am not going to enlighten him because we can't define this word too precisely. We really cannot define it too precisely. So let us give examples and see what we mean by random strings and so on. One way would be to say a random string consisting of two letters L's and R's, you would say is a string where there is absolutely no pattern. This is one way you might want to define it. By that I mean the probability with which, or you take a long part of this string and you ask how many L's are there and how many R's are there. If the answer is exactly half, the fraction is near 50% each, you would say okay, at that level this string is random. But then I could say suppose all the L's occur first and all the R's, that is not true, this is no longer random, it is completely periodic. This thing here, it really does not look like a random sequence at all. And then you say okay, the a priori probability of having an L or an R after you say have a million digits, the million and first digit, 50-50, then you would say it is random. In other words, if there is no correlation which you can detect, the number of times L's appears is on the average the same as the number of times R's appears, the number of times the sequence LL appears is the same as the number of times RR appears, or LR or RL, 1/4 each of these. The number of times a sequence of 3 L's appears together is the same as the number of times any other sequence of 3 letters appears, etc. So if all these correlations are missing, if you say these are, then you would say okay, now we are approaching something like a random sequence. But it is again tricky, because you could have within randomness, you could have something very regular like the digits of pi. The digits of pi, if I write it down, or any transcendental number of that kind, if I write this number down, then it looks like the digits, successive digits from 0 to 9 appear completely randomly. So if you take a billion digits of pi and ask how many times does 0 appear, or how many times does 1 appear and so on, these are all roughly 1/10. If you ask how many times does the sequence 27 appear, it is the same as the number of times 72 appears or 63 appears, it is of the order of 1 over 100. So it looks like the whole thing is completely random. On the other hand, if you give me a million digits of pi, the million and first digit is completely determined because I have an algorithm for computing pi. So what do you mean by randomness here? Therefore we have to be much more careful and start asking what kind of randomness are we talking about? Are we talking about lack of correlation? Are we talking about a priori probabilities and so on? And if you think about it a little bit harder, you discover that there is no truly satisfactory way of defining randomness at all. And the lesson I want to, without getting into that kind of meta mathematics, the lesson I want to draw here is that chaotic time series, this is after all a time series here, could look quote unquote just as random as a truly random time series. We will not go further into this for the moment, we will keep this at the back of our minds that no pattern need be discernible at all, could be completely quote unquote random. Again I put this word random in quotations, yeah.
So if you take any random set of
Yes.
coin tosses,
Yes.
will you be able to find a initial condition which will give you a
Yes,
sequence?
that is the statement. I take any random set of the result of any set of any coin toss experiment, then the statement is there exists an initial condition for which the successive iterates would give you exactly that sequence. So in that sense you can put these into correspondence with each other. Now let us get on with this, let us see, okay, now that we know that chaotic dynamics in some sense could be very random looking in this restricted sense, let us see what we can do with it. We would like to find some measures for these this kind of chaotic dynamics. So what can one do? One should ask, alright, if I have more complicated alphabets or symbolic dynamics, I take my phase space, I break it up into cells, then can I reconstruct, by looking at the sequence of letters, can I reconstruct the dynamics? And in this case we could. So this example that I gave with just 2 L's and R's here, just 2 cells for the Bernoulli map, is called a generating partition. In other words, I broke up the phase space into 2 cells, I partitioned it and kept track simply of whether the point was in the left cell or the right cell, and I generated a string, but that string has in it the full information of what the initial condition was. I can reconstruct from that string where I started, I can reconstruct the dynamics, and that kind of thing is called a generating partition. And one of the aims of chaotic dynamics would be to try to get a generating partition, after which you do not have to look at the actual dynamics, but you need only look at the dynamics of these symbols, of these letters, and that goes under the name of symbolic dynamics. Suppose we have such a partition, and we are going to talk about several kinds of partitions now very shortly. Suppose we have such a partition, and I am going to take very specific examples. So let us go now and look at a phase space which is perhaps in a one dimensional map, the unit interval for example 0 to 1, or it could be more general, and I break it up into little cells and keep track of where the system is. That is all I do at each iteration. So in some sense I coarse grain my phase space, my resolution is not at the level of a point but rather of a small interval, and I simply ask, is the particle in this bin or that bin. And more general phase spaces, if I have a multi-dimensional phase space, I imagine doing something like this. I break it up into various cells, and suppose this is cell C sub j, I label it with a j, and I also assume that there is an invariant measure for each cell, namely if there is an invariant density for this process, the chaotic dynamics, then the integral of that density over the volume of this cell. I will call that the invariant measure, and let me denote it by mu sub j. This quantity here is the invariant measure of cell Cj. Okay. Then is there some way in which I can understand from the symbolic dynamics, is there some way in which I can quantify the actual dynamics. In other words, there could be some cells which are visited very often, there could be some cells which are visited very infrequently. Is there some quantifier by which I can probe this? There could be some cells which are weighted very heavily, which have a high mu j, and there are others which have a low mu j, and I assume that each of these mu j's is a non-negative number between 0 and 1, and the total measure is 1. If I normalize everything, the total measure is 1. Then we define the following set of numbers which helps us do this, and this set of numbers is called the set of generalized dimensions, and it is defined as follows. I introduce a parameter q and write d sub q, this is the generalized dimension, the qth dimension. Q is a number, a real number, and it plays the following role. This is defined as the limit in which the size of each cell goes to 0, and let us for simplicity assume that each cell is of some size epsilon. They do not have to be of the same size, but it is completely arbitrary how I partition it, but I would like to look at the limiting case, because finally you would like to go to the dynamics of the point itself, and therefore the cell size should go to 0 eventually, but formally let us write limit epsilon goes to 0, that is the linear, the dimension of a cell, the size of each cell, of the following: 1 over 1 minus q, the reason for this will become clear, the log of a summation from j equal to 1 to the total number of cells, and that is a function of the size of each cell. So let us call capital N of epsilon the total number of cells into which my phase space has been partitioned. The log of this sum of mu j raised to the power q, divided by log of 1 over epsilon. So let us consider this quantity, where q is a real number. We could start with q an integer and later continue to all q's, all real numbers from minus infinity to infinity, but let us study this, let us define this quantity and see what it is trying to tell us. If I set q equal to 0, d0 is the following: its limit epsilon goes to 0, this becomes q equal to 0, log of, if q is 0, this thing becomes 1 here, and it is just the number of cells into which you partition things. So log n of epsilon over log 1 over epsilon. And what is this quantity? What is it telling us? This quantity is called the box counting dimension of this set, and it is the fractal dimensionality of the set of this attractor or whatever phase space you are looking at here. Now I should have mentioned earlier that I have in mind a situation where the system has fallen into some chaotic attractor, some region where it is completely chaotic dynamics. So all the transients have been removed, and I talk now about the stationary distribution, that is why I use the invariant measure here. So all transients have died out, and now the system is continuously going on this strange attractor perhaps, or the unit interval in the case of these maps which are chaotic. And this is the fractal dimension or box counting dimension of this attractor. So let me explain what I mean by that. Many fractal dimensions here, but this is the first of the lot. Now I should spend some time and take a little digression and talk about fractals. Since we have sort of mentioned this word fractal several times without actually defining it, I ought to do that now. Time has come when we need to do this. But first I want you to notice that the following fact, which I will come back to: this quantity here if q is positive, then clearly this number dq is going to be dominated by those cells for which the mu j is large relative to those which are where it is small. In other words, when q is positive, dq will be heavily dominated by those cells which are visited very often. So the total fraction of time spent there will be larger, in other words mu j is larger for such cells. On the other hand, if q is negative, it is just the other way about. Those cells which are infrequently visited would contribute to this number dq, and those which are more frequently visited would not, because this would then become a negative number here. Q becomes a negative exponent. Therefore the smaller mu j's would dominate over the larger mu j's. We keep that in mind for a moment, and at q equal to 1 we seem to have a problem, really seem to have a problem, because this blows up. On the other hand, if q is 1, you end up with summation j equal to 1 to n of mu j, but that is the total measure which we have taken to be unity, we have normalized it to be unity. So you get a log 1 there which vanishes, and you get this which vanishes, and the question is there a limit or not, and we will see there is a limit, definite limit, which will be a surprising limit, okay, and so on for higher values of q, etc. But now with that, let me come back, let us backtrack a little bit and give a little quick tutorial on fractals and what we mean by fractals. The traditional way of doing this now is to go back and look at fractal lines. This has been around for a long time. Mathematicians have known about fractals for a very long time, but only after the 1960s and 70s, when Benoit Mandelbrot introduced the term fractal into the physics literature and started applying this to various physical problems, this became extremely popular and almost fashionable. Today we have fractal art and fractal dimensionalities everywhere, fractals everywhere, the titles of popular books and so on. And what do we mean by this? And the simplest way of doing this is to give you simple examples of this. So let us look at, for example, a line of this kind, a smooth line. Does not have to be really smooth, it could have corners and so on, and ask what is the length of this curve. That is a traditional way to introduce fractals. Now the length of this curve is measured in practice by putting little foot rules everywhere, little meter scales everywhere, and adding up all those pieces. Now if you have, for instance, we know this thing has some finite length in some sense, and I take a meter rule and start measuring its actual length, then you are well aware intuitively that this length has some absolute value independent of the size of your ruler, certainly should. It does not matter whether you measure it in centimeters or meters, it has an absolute value. If its length is 1 meter, you would discover it is equal to 1 if you expressed it in meters, it is equal to 100 if you expressed it in centimeters, 1000 if you expressed it in millimeters, but the fact is there is an absolute length to this curve. And that is because the assumption is that if you measured it with a foot rule of resolution this much, then the number of such things we would put in order to measure it, etc., would give you, in this unit, would give you a certain number. But now if you use a smaller ruler of this kind, you would need more of these guys, so the actual number would become larger, but then the conversion between this and that would give you the same actual absolute length, provided the curve is smooth. On the other hand, imagine what happens if the curve has kinky corners of this kind everywhere. Then if I have a curve which is very jagged of this kind, very roughly in this fashion, and I use a resolution of this much, then this entire curve from this point to this point is just put in, subsumed under 1 unit, because in some sense this ruler is too coarse to see these little bends. On the other hand, if I start using a much finer scale, then indeed I will be able to put this here and then this here and this here and so on. So I really call it as 3 of these smaller units as opposed to a single one of the bigger units. I miss those little bends in the curve. This suggests immediately that this curve's length, the actual length, depends on the resolution that you have, and if the resolution is L, then the actual length L could be a function of little l, the length that you measure, and this is not choice of units that I am talking about. The actual length, the absolute length that you measure would be equal to some constant which depends on the units that you choose, and it could well diverge as this little l goes to 0, like L to the power d. It could well diverge, it could actually tend to infinity if you had little kinks and corners on all length scales right down to 0. So it is evident immediately that if the absolute length of a certain curve is to diverge, it means it must have a large number of bends which are missed if you have a resolution which is too gross or coarse. So if indeed you can construct a curve which has kinks and corners everywhere on the curve at all points, then if such a thing can be constructed, its absolute length would actually become infinite as your resolution goes to 0. So this would look like this as L tends to 0, it would diverge like some power of L, some negative power of L. That power with which it diverges, this thing here, is called the box counting dimension. Box because the same thing can be generalized to higher dimensions like 2, 3, 4 and so on. We are talking about a one dimensional curve here. So this d here is called the fractal dimension or the box counting dimension of this curve, and we will see by examples that this curve, this d need not be an integer. The topological dimension of this curve is 1 for any curve, just as the topological dimension of a surface is 2, of a volume is 3 and so on, of a point or set of points is 0. The topological dimension of this continuous curve is actually 1. However, this dimensionality could be a number between 1 and 2, it could even be 2. It could even be as big as the dimensionality of the Euclidean space in which you have embedded this curve, in this case the blackboard, namely 2, it can't be bigger than 2. So you could have a curve on this plane which is space filling, namely it comes arbitrarily close to every point in this plane and may even intersect itself, and such a curve would have a dimensionality of 2, a fractal or box counting dimensionality of 2. But in any case it could be some number between 1 and 2, and then we call it a fractal curve. And let me give an example right away of how you compute fractal and the fractal dimensionalities. And this example is called the triadic Koch curve, and it is specified by a geometrical recursive construction in stages. So you start with a unit length 0 to 1 at the first stage. At the next stage the construction is break it up into 3 equal parts and tilt the middle part upwards. So this goes into something which looks like this. So this is still 0 to 1, but this is 1/3, that is another length 1/3, that is another length 1/3, and that is another length 1/3. So you are still between 0 and 1 except you moved up in this fashion. So the total length of this curve in some units has become 4/3 from 1. Each of these is 1/3 the original length. At the next stage you do it all over again for each of them. So now how many pieces do you have? You have 4 here, 4 here, 4 here and 4 here. So at the first stage you had 1 piece, then you had 4 pieces, and now you have 16 pieces, and each of these is 1/3 of this. So what has happened to the length? Yeah, it has become 4/3 whole squared and so on, and it is evident if you keep doing this forever that this whole curve will still occupy a finite portion of this plane, it will start at this point, end at that point, but its length would actually become infinite and you would have these corners everywhere. So it would become differentiable, non-differentiable almost everywhere, its actual length would become infinite, it would have a corner everywhere, and you could now ask what is the fractal or box counting dimensionality of this, namely how does it diverge, how does this length diverge, and a moment's thought will show you, and I want you to work this out, that the length at any stage is going to increase geometrically, increasing like 4/3 to whatever power of the generation or the number of iterations, and it actually becomes infinite, and you can now ask how does it become infinite as the size of each of these pieces goes to 0, and that power is the fractal dimensionality, and a moment's thought shows you that this d here, which after all if you take the resolution to be little l, then it is going like L to the power minus d, and therefore what you should do is to take the log of that and divide by the log of L, and that will give you d. If L of L goes like constant divided by L to the power d, in order to find this d all you have to do is to take logs on both sides and then let the limit L go to 0. So it is not hard to see by this regular construction that this is also equal to log. In this case I do not have to take the limit epsilon or little l goes to 0, because this procedure is generating a regular fractal, in the sense that the relation this bears to this is the same as the relation this bears to this, and so on at each stage. So all you have to do is to ask, given this construction at some stage, what does the next stage do, how much does it increase the length by, and that will give you an indication of what d is. So a moment's thought will show you that this is the same as the log of the number of pieces into which you break the system at any stage divided by the log of the ratio of the size of each unit at one stage to the unit at the previous stage, and in this case this was 1/3 of this, and therefore it is log of 1/1/3, and that is log 3. So if the demagnification factor is 1/3, then it is log of 1 over that factor, and in the numerator you have the log of the amplification factor, namely each unit here gets broken up into how many pieces here, and what is that equal to in this case? It is 4, in this case it is 4. So this is equal to log 4 over log 3, and this is greater than 1 but less than 2. That is the fractal dimensionality or box counting dimensionality of this fractal curve. This construction for all regular fractals, you can decide now what the fractal dimensionality is, namely how does the measure, the length or the volume or the surface or whatever it is, diverge as the size of each box unit goes to 0, by simply writing down the ratio of the logs of the number of pieces into which the previous steps unit is broken at each stage divided by log of the reciprocal of the demagnification factor. And I leave you to play with this, because you can have all sorts of fractals, you can construct all kinds of fractals. If you look at textbooks, books on fractals, they give you a huge number of geometrical constructions where you would see the calculation of these fractal dimensions done in these cases. But that is exactly what we have here. This is exactly what we have for d cube when q is 0, because you are breaking up a system into cells and you are letting the cell size go to 0 each time, and then the ratio of the log of the number of cells of dimension epsilon, of size epsilon, divided by log 1/epsilon, because epsilon is the demagnification factor, is in fact the fractal dimension of this set. Now depending on what this the original phase space is, what the attractor looks like and so on, this number could be a fractional number, it need not be an integer at all. So it is some number which tells you what the fractal dimensionality of the attractor is. Could be a set of points with a fractal dimensionality between 0 and 1. This is possible. I will give a construction very shortly to tell you what the fractal dimensionality of a set of points is. We talked about the fractal dimensionality of a curve here, a one dimensional, topologically one dimensional object. But now let us look at the following construction, and this is called the triadic Cantor set. So that is another very common fractal. This is called the middle thirds Cantor set, and the construction goes as follows. It says take the unit interval 0 to 1 and remove from it open interval, the middle third open interval. So here is 1/3, here is 2/3, and at each step in the construction remove the middle third thing. So remove 1/3, 2/3, remove this open interval, leave the point 1/3 here and 2/3 here, they belong to the set, but remove the points in between. So where does it get us? That gets us to this. So I have this and I remove the middle thirds. In the next step I remove the middle 1/3 for each of these, and where does that take us? So it looks like this, and there is a big gap. So this was 0 and that was 1, but just as I had a 1/3 here, this is a 1/9, that is a 2/9, that is 3/9, that is 6/9, which is 2/3, that is 7/9, that is 8/9, and that is 9/9. Then I continue this forever and I keep doing this. Each time I remove the middle third open set. What am I left with finally? I am left with a set of points. I am just left with a set of points. Now what is the total length of this set of points that I am left with?
0.
The length is 0. How do I assert that? How do I assert that?
Because the length at every stage is decreasing.
No,
Yes.
and whatever,
Okay.
if you find
So what should
something,
be-
you have to cut it anyway. So it
Yes.
will come. So there's
Well,
no,
how
nothing
am I
of finite
guaranteed that
length.
the length finally is 0? I mean, how do I know that?
As limit tends to 0.
Because that's from the
this will
rules,
be
sir.
The ratio of any successive
Yes.
step is lesser.
Yes,
And as n tends, it is infinity.
absolutely. So you can see that you are reducing the length by a factor 1/3 each time, 1/3 of it is gone, and as you go to infinity the total length is 0. I urge you to work this out. I urge you to work out what the length is after n such iterations. Yeah, it is 2/3 to the power n, and as n goes to 0, that goes to 0. So it is clear that the actual topological dimension, the measure, the Lebesgue measure of whatever is left is 0. So it is a set of points. Now is it a countable set of points or uncountable? It is an uncountable set of points. It is just a set of disjoint points, but it is uncountable. Okay. So it is an uncountable total equal to 0 in the limit. What is the fractal dimensionality of this set? And that is almost by inspection, because instead of adding something you are simply removing something. So what is the fractal dimensionality of this set? So what is D? Exactly. So you are breaking up each unit into 2 units. So n of epsilon is in fact 2 at every stage. So this is equal to log 2. But then each unit, new unit, is 1/3 the original unit, and therefore you have log of 1 over 1/3, and that is log 3. So this is log 3 here, and this number 0 less than this less than unity, it is a fraction.
So the lower limit is not 1, it's actually the number of dimensions minus 1. What is the lower limit in most general case?
The lower limit could be, yeah, exactly.
Number of dimensions minus 1.
The number of, if I start with a curve, yes, that is true. If I start with a plane and start, depends on the construction that I do to get rid of things, yes. It is a fractal dimensionality which lies between the topological dimension of this object, right, and the Euclidean dimension in which you buried, this is of the space in which you have embedded it. So in this case it is some number between 0 and 1, and it actually gives you some indication of what the nature of the set is. Now this was easy to compute because we actually looked at, we didn't go all the way to infinity, we didn't take this recursion indefinitely far, but we realized that this whole curve is self similar, exactly self similar, in the sense that at any stage the relation the curve bears to its immediate preceding stage is identical as you go along everywhere. So it is self similar, but then real fractals which occur in nature could only be statistically self similar, in the sense that be very irregular objects. There needn't be this kind of regular construction that takes you from one stage to another which does not change at all, and it could be, its statistical properties could be exactly the same at all stages, but does not have to be actually physically self similar, not a geometrically regular fractal at all, could have very irregular motion such as diffusive motion or Brownian motion and so on. These things are statistical fractals, but the formula for the box counting dimension is precisely what I wrote down, which is limit epsilon goes to 0 log n of epsilon divided by log 1 over epsilon. Okay, so much for quick tutorial on fractals. We will come back to this a little bit later. Now going back to our, yeah,
Your
question.
definition of fractals was the length is symmetrical.
Pardon me, yeah, it diverges, the length will, of such objects will diverge, or if it is a,
In this case it is not so.
pardon me, but then I am not talking about a fractal curve here, it is a fractal set of points here.
What exactly is the fractal number? No, you said the length becomes infinite, right? But in the last case you told that the length set by 0, your total.
Okay, his point is, I defined my fractal by saying, I started with the example of a curve and I said this curve is going to have an infinite length eventually, and now in the set of points there is no length. From the curve I could go to higher objects like areas, volumes and so on and so forth. The scale, it is a question of how it scales. So now I generalize that and say that I define my D as the scaling exponent, nothing more than that, in the limit in which the size goes to 0, and that is all. So it has no connotation of being a length diverging or anything like that, it simply says what is the scaling exponent, namely how does, you see, if D equal to log n of epsilon over log 1 over epsilon, this implies, if you imagine, I forget about the limit for a minute, then it says D log 1 over epsilon equal to log n of epsilon, which implies that n of epsilon scales like epsilon to the minus d. Now that is all I am interested in, that is how I define my fractal dimensionality. So it is just a scaling exponent, nothing has to go to infinity or anything like that.
That is a fractional dimensionality.
Exactly.
What is the fractal?
What is the
Fractal.
A fractal is a geometrical object which has a non-trivial fractal dimensionality, which is different from its topological dimension. In this case it was a set of points, the topological dimension is 0, but this dimension is some number between 0 and 1. It's some, could be less than.
Could it be lesser than the topological dimension?
Do you think it could be less than the topological dimension? Not the way we have constructed these things. No. And it can't be greater than the Euclidean dimensionality of whatever space it is embedded in, certainly. So those are put bounds on it. So now there are plenty of examples. For example, if I look at this surface and I pretend to look at it at greater and greater magnification, then it would become irregular on many scales, it would become more and more rough, and the actual total surface area could well tend to infinity. Now physically, of course, that is not true, because you soon come to a stage where the physics of the problem gets in and things are no longer fractal, because the very structure changes. I mean, once I get to the level of atoms, for example, then it is not even a continuous surface at all. So there is always a lower bound and an upper bound in from physics, from physical considerations of when things scale in this fashion. So clearly, if you look at a very classic example would be coastlines of countries, and this is how Mandelbrot originally introduced this whole business. How long is the coast of Britain, or how long is the coastline of a country? Well, if you look at it from 100 kilometers up, then the country seems to have a coastline which looks like this, but you get closer, then the coastline is actually larger, because now you are going to start looking at structures on smaller scales. Eventually you would start counting, how do you define a coastline? Suppose you say it is all those portions of the coast which are not wet, or which are wetted, the boundary between the water and the land, then you would have to start looking at individual boulders and then individual rocks to see if it is part of the coastline or not, and of course the total length is increasing. Then you start looking at individual grains of sand, and some would be wet, some would not, partially, and so on. But of course once you come down to extremely fine scales like atoms, we know that this is not even a continuous curve, so it is gone, right. So it is obvious in all these cases that there is a lower scale, lower resolution and an upper resolution within which the system is fractal, and beyond it it is not. Although mathematical fractals of this kind, like the Coarse curve and so on, the assumption is it is a geometrical construction, so it goes right down to epsilon equal to 0. So we must keep that in mind, that in physical applications there is always some orders of magnitude, or range of orders of magnitude inside which the system is fractal. Okay. So let us go back and examine dq. We are going to come back and compute this in many cases. So this is limit epsilon goes to 0, 1 over 1 minus q log summation j equal to 1 to n of epsilon mu j to the power q divided by log 1 over epsilon. Okay. Now we can start computing this in simple instances just to see what things look like. What would happen if I took, for example, the Bernoulli shift and I did the following. Here is 0 to 1, and in this case I am just going to break it up into a finite number of, into a certain number of cells, and let the resolution go to 0, the number become larger and larger. So let us break it up into n cells, each of length epsilon. So n is simply 1 over epsilon, nothing more than that. And what is the invariant measure for this map? What is the invariant measure for the Bernoulli shift? It is a constant, and therefore what is mu j? Every mu j is exactly the same. This is equal to an integral over Cj dx rho invariant of x. That is the natural invariant measure for each cell, but rho of x is 1 for the Bernoulli shift or the tent map at fully developed chaos, and therefore this is simply equal to the length of this cell and nothing more than that. And what is that equal to? Just epsilon. Each of these is epsilon, nothing more than that. So what happens here? What happens to this definition? It becomes trivial, right? So this is equal to limit epsilon goes to 0, 1 over 1 minus q, then what do you get up there? This is constant, right? Yeah, so this thing here n, that is the total number, and it is exactly the same for each of those guys. So what does it give you? Yeah. N epsilon to the q, so log n epsilon to the power q right there divided by log 1 over epsilon, this fashion, nothing more than that. And what is that equal to? So let us write this as log n plus q log epsilon, this guy. What does that give you? So if you like, write this as q minus 1, write this as log epsilon. So what is log n? Remember that n epsilon in this problem equal to 1. Yeah, but can't depend on epsilon.
Q minus 1.
1 dq is 1.
So what does it give you? dq is what?
Same as a dimension.
Yeah,
Euclidean.
Yeah.
Euclidean dimension and the fraction.
yeah. So what do you get for dq?
1.
1. This is such a trivial problem. You had a unique, you had the unit interval, we broke it up into equal cells, we let the cell size go to 0, and it simply says this is such a simple problem. I mean the invariant measure does not distinguish between one part of the phase space and another, that all the dq's have turned out to be 1, every one of them is 1. It is not giving you much information, and this attractor has the dimensionality same as the topological dimensionality of the interval itself, it is 1. So it is really not strange, it is not a fractal dimension in that sense, it is an integer, it is 1, and it is a very trivial problem in this case. Now would the same thing happen if you had, for instance, the logistic map at fully developed chaos? It won't happen that way. Even if I broke it up into equal size cells in exactly the same way, it is clear certain cells near 0 and near 1 would be heavily weighted because the invariant measure is very large there and much smaller elsewhere. So I leave it as an exercise to you to calculate dq in that case, and it is not a trivial matter, it is a function of q now, but you have to be very careful in doing this because, so take for the logistic map at mu equal to 4, we know that rho of x equal to 1 over pi times square root of x into 1 minus x, and then what would mu j be? What would mu j be if I took the unit interval and broke it up into equal parts of size epsilon each? So this number is epsilon, this number is 2 epsilon, and so on. Or if you like, I break it up into n cells, this is the same as 1 over n, 2 over n, etc. So the mu j cell, the cell Cj, this is the interval between j minus 1 over n and j over n. Therefore mu j equal to integral j minus 1 over n to j over n of dx 1 over pi square root of x times 1 minus x. You have to evaluate this integral and then you have to raise that to the power q and then do this construction here. In this case n of epsilon is just 1 over epsilon, or if you can replace this down here 1 over epsilon by just log n here and work with just n, because everything there is written as a function of n, and then you have to compute this. So we are left with the problem of computing this quantity 1 to n mu j to the power q divided by log n, and mu j is this quantity here. Now one might be tempted to do the following, and here is where you have to be careful. One might be tempted to say that this quantity here, the sum as epsilon goes to 0, is really going to some kind of integral. So you might be tempted to replace this summation by an integration of the form dx rho of x to the power q. over the full interval from 0 to 1. So this quantity here is related to this integral here, but you have to be very careful here, because this thing here, because the invariant measure has that structure, is of the form x over q over 2 1 minus x q over 2, and this does not converge. This does not converge if q is sufficiently large positive. It is immediately clear that if q is bigger than 2, if it is equal to 2 also you have a problem, because then you have dx over x and that is logarithmically divergent. So this replacement of the sum by an integral will work only if q is less than 2, and so you immediately begin to see that at q equal to 2 you have an abrupt change, something happens and you no longer can replace the summation by an integration. On the other hand, the summation can be well defined, this quantity is well defined absolutely, and you therefore have to treat this separately. You have to leave the sum as it is for q greater than equal to 2, and for q less than 2 you could replace it by a suitable integral. So that is where the non-trivial arithmetic comes. I leave you to do this analysis. Next time I will write out the solution for what this is and how to go about this. So you can immediately see from here that dq need not be a constant, it will change. By the way, what do you think d0 is in this problem? What do you think d0 is, even in the logistic map? What do you think d0 is? It is in fact the fractal dimensionality of the attractor, which is equal to, which is 1, because it is the full line, right, its Lebesgue measure is 1, so it is actually the fractal, d0 will turn out to be 1 definitely, but as soon as q exceeds 2 you have a problem. So you need a function which will be 1 at q equal to 0, but something else at q greater than 2, greater than equal to 2. Now let us, we will come back to this, but let us look at what d1 is, because that is non-trivial. We need to be able to write down what d1 is and then physically interpret d1. How do I do that? What should I do? I need to find the limit of these quantities as q tends to 1. So let me write this as d1 equal to the limit as epsilon goes to 0, limit as q goes to 1, limit epsilon goes to 0 of this quantity here. Need this. And the question is, what am I going to do this? So let us find out what this quantity goes to. After all, the numerator goes to 0, the denominator goes to 0. So what should I do? I ought to write mu j to the power q as e to the q log mu j, and do a Taylor expansion of this function about q equal to 1, because there is a q minus 1 sitting here. So terms which are quadratic in q minus 1 will disappear, and all that will survive is the quantity that the coefficient of q equal to 1, right. So this thing here is equal to e to the power q equal to 1 is e to the log mu j plus q minus 1, the derivative of this quantity at q equal to 1, which is log mu j e to the log mu j plus order q minus 1 the whole squared, and that gives me e to the log mu j is just mu j plus q minus 1, and this is mu j log mu j plus higher orders which you can ignore out there, and I have to do the summation of this from 1 to n. So let us do that. So sigma j equal to 1 to n of epsilon is the summation here, summation over j, and that gives me a summation over j of this thing here, but that is equal to sum over j mu j is 1 plus q minus 1 comes out, sum over j mu j log mu j plus higher orders. Now I have to do a log of the whole thing. So what does that give me? Log summation j equal to 1 to n mu j to the q therefore is equal to log of this whole thing 1 plus sum over j equal to 1 to n 1 plus q minus 1 sum over j equal to 1 to n mu j log mu j plus higher orders, and I want the leading term at q equal to 1. So I have log 1 plus z, and what is the series for log 1 plus z for small z? It is z plus z squared over 2 or minus z squared over 2 plus etc. etc. So the leading term is just z itself, which is q minus 1 times this, and therefore we have a formula now for d1 which is equal to limit epsilon goes to 0 1 over, so we have something here which goes like 1 over 1 minus q, and then you have a q minus 1, so they cancel each other and you end up with summation j equal to 1 to n mu j log, and this is n of epsilon mu j log mu j divided by log 1 over epsilon. With a minus sign because this was a q minus 1 and this was a 1 minus q, okay. Therefore this could be written as log log mu j say, but you could also write this as log epsilon. Does this remind you of something? Reminds you of entropy, for which if you have many possibilities and if you have a set of events with probabilities p1, p2, p3 etc., you know that there is something called the information and there is something called the negative of the information which is the entropy, which is something like summation over I pi log pi, okay, and that is exactly what it is, except the probability is being replaced by the measure of the cell, again a number like between 0 and 1. So in fact mu j gives you the a priori probability of being in cell j. If you start completely randomly and put your pencil there according to the dynamics, then mu j tells you that the typical point will inhabit cell j with probability mu j once you are on the invariant attractor. So it is very much like information or entropy, and d1 is called the information dimension, just as the earlier one was called d0 was called the box counting or the fractal dimension, this is called the information dimension. This is the only value of q for which you have a log sitting there, and that is because of the special way in which q equal to 1 led to this log immediately, because summation over the measure mu j gives you 1 when you sum it. So it ended up with this log. It is not true for any other q, you do not get these logs for any other q, because mu to the power j would be perfectly to the power q would not reduce to 1 in that case. So that was the reason for putting the 1 over 1 minus q, to make a finite limit here, you need this, and of course at q equal to 0 it does not matter. Okay. Now I leave you to find out what d1 is for the logistic map. In fact you would like to find out what dq itself is for the logistic map. A result which I will quote, which I will not prove, is the following: if q prime is greater than q, then dq prime is less than equal to dq. In other words, dq is a non-increasing function of q, it generally goes down or could remain constant for a while and then go down and so on. So this is not hard to prove, it is actually provable from the definition of dq itself. Again I would like you to try this out and see if you can establish this, it is fairly straightforward to do this. Just the property of the measure is needed, the fact that the mu j's are non-negative numbers between 0 and 1, that is all that is needed. Okay. Now where does this get us? What does it all get us? Well, we are going to look at some partitions. I have run out of time today, but we will look at some partitions of simple maps, and we will push this idea further that this chaotic dynamics is starting to look more and more like the realizations of some random process, some suitable random process. So what I will do next time is to show you that you can partition the phase space in such a way that the jumps of the representative point from one cell to another would not look different from a Markov process, and therefore you could use the machinery of Markov chains in the theory of random processes in order to understand what the dynamics looks like at the coarse grained level. So this is bringing together deterministic dynamics with stochastic or random dynamics, and it becomes very interesting to analyze the system from this point of view. So we do this next time.